so we got, looked like we had some decent stuff on 19, on 23, on 25. Those are the big ones. I mean, those are the ones that we want to mimic, what we did yesterday when we did number 20, we did number 24. Quiz, you're going to have to be able to do that. You're going to see those kind of problems over and over again. Going through this process that I have up on the board right here. Okay? And so those are really important. Now, all the other ones are important too. That 3 through 12, that 3 through 12 is just stuff like we did in chapter 1, right? It's just that we have this new notation called big F, which is the antiderivative of F, so big F and little f have the same relationship as F and F prime, right, on the chart. So we got to be able to just answer those same questions. So we'll talk about those a little bit too. But I just put this together just to, again, see the difference between local max min and global max min, and what I call chart stuff. Local max min, inflection point, which I've thrown on here as well, etc. All that concavity, increasing, decreasing, all that stuff we do with the number line. Whereas a global max min is a little different kind of question, but they're closely related in what you do. In both of them, in both of them, you start with doing the derivative and set it equal to 0. So let's say I had an F graph, but normally we don't. We have equations, but I wanted to show you a graph just so you can see like the local max, local min's inflection point stuff. But usually what we have is an equation. Okay, so your job, if you're finding local max min, is do the derivative, set it equal to 0. Find the stationary points. And then you put those on a number line. Now, what we didn't do yesterday, I don't think there were any problems about inflection points, were there, other than in that graph one at the beginning. But, right, we're going to get into somewhere we have to find inflection points also. We're going to do some of that today. Well, then what you do is you do the second derivative and set it equal to 0, right? Because that's what the chart tells you. The chart tells you second derivative, tells you about concavity of that. So you do the second derivative. So you do the second derivative, set it equal to 0, solve that, and you put that on your number line. Those are possible inflection points, right? So the first derivative equals 0 is stationary points. Second derivative equals 0 are possible inflection points. So you put that on the number line. Now let's just look at this and see if we all understand what's being said here. So if I get this number line, and we pick numbers in between, we plug those into F prime, we get positive or negative. We pick numbers in between, plug those into F double prime, and we get positive or negative. Okay, now, what would this tell me about the F graph right here? The F graph's increasing, decreasing, increasing, decreasing. So increasing, decreasing, we got local max, right? Decreasing, increasing, we got local min. Increasing, decreasing, we got local max, right? So all those questions about increasing, decreasing, local max, local min can all be answered by this number line, right? Now, what does this tell me about the F graph? F double prime negative, concave down. And then what's this tell me? I should be pointing at this. People watch. What's this tell me? Concave up. Concave down. So what's that tell me about 3 and 5? They are inflection points. But if this would have went negative, negative, would 3 be an inflection point? Because it'd be concave down, there wouldn't be a change, right? So concavity and inflection points are told by that number line. Does that make sense? So that's why I call that chart stuff. Because if you look at the chart, that's everything. Increasing, decreasing, local max, local min. We would know if we have a flat spot, concave up, concave down, right? If the second derivative is positive, concave up. Second derivative negative, concave down. Second derivative 0 is a possible inflection point. We got to see if it changes concavity. So everything in here, right? Everything in here is shown on these, with these number lines right here. By doing the derivative, setting equals 0, doing the second derivative, setting it equals 0, making these number lines, we can tell everything about what the graph's doing on the chart. Okay? So, then you've got your global max min problems. Okay, a global max min problem, we want to know the highest and lowest point. Now, in this one, it looks like the highest point is here, looks like the lowest point is here, right? But how would we know that if we didn't have a graph? If all we had was an equation and you couldn't use your calculator, right? Well, what we would do is we say, well, the highest and lowest points have to either be at the endpoints or they have to be at the stationary points, right? They have to be at the local max mins or they have to be at the endpoints. So we do the derivative, set it equal to 0, see what those points are. Well, that's 2, 4, and 6. right? We have a stationary point at 2, 4, and 6. So we want to find those stationary points, which of course is the same thing we want to do over here. So we do the derivative, set equals 0, get those points. Then we get our endpoints, which in this problem is 1 and 7. Then we take all 5 of those and we do what with them? Plug them back into the original, right? Because what we're wanting, and that's called our list of candidates, and we want to see what the y values are. Well, it turns out the y value at 2 is going to be the highest one. The y value at 7 is going to be the lowest one. That's going to be our minimum. Over here, we were plugging into f prime and f double prime, right? Because we were making number lines, so it was different. Here, we were taking these numbers in between, and we were plugging them into f prime to see if f prime was positive or negative. We took these numbers in between, plugged them into f double prime, because we wanted to see if it was positive or negative. But over here, we're taking our candidates, our possible places of our global max min, and we plug them into the original function, like so. Okay, so that's the deal there, all right? So let's go and work on, let's skip over this one and let's go right to 19. So I just want to quickly go through this because it looked like a lot of you had some stuff here. So on 19, we're going to do the derivative. We're going to factor out a 3x. We're going to find our 2 stationary points are here. So I'm going to pick some points in between. I'm going to plug those back into f prime. I like that version better to plug into because I can tell positive and negative. Remember, I don't really care what the value is. I care if it's positive or negative. So if I put a -1 in here, I'm going to get negative out here. -1 minus 2 is -3. Negative times negative is positive. Put a 1 in here, that's positive. 1 minus 2 is negative. Positive times negative. Put a 3 inside the parentheses is positive. That'll be positive. Then I don't have to work it out up here, right? So whenever you're doing a no calculator, a lot of times you're doing some factoring. It's really easy to plug it into that factor version to get your positive and negative. Okay, well now I can answer all the questions that 19 asks. Where's the function increasing? Negative infinity to 0, 2 to infinity. Where's it decreasing? 0 to 2. Where's the local max? We have a local max right here at x equals 0. We have a local min at 2. And don't forget what I said on that local max. You've got to say local max. If this was a test, you'd have to say local max at x equals 0. And you'd have to say y. You say f prime changes positive to negative, so f changes increasing to decreasing. You with me? Make sure you have that. I'm not sure I saw it on everybody's paper today. I will not be writing that down most of the time when we're working them up here anymore, right? I will just mention, make sure you give your justification. F prime is changing positive to negative, so f changes increasing, decreasing. That is why there's a local max at x equals 0. Gotta have it, gotta have it, gotta have it. Okay? That's going to be worth a point for sure. This problem probably worth a point for the derivative, maybe a point for setting it equal 0, maybe a point for solving it. I don't know, that might be 2 points or 3 points right there. A point for a proper number line, so that can be a 4th point. Identifying your local max or min could be a 5th point. The justification could be a 6th point, right? Or something like that. There could be a lot of points right there. Okay, you got to show those steps, right? If this was a calculator problem, everything would pretty much be the same. You might not have had a step right here where you did this, and then when you went to plug these numbers in, you could just plug them in on your calculator, but you'd still have your number line, you'd still have this, you'd still write down your stationary points, you still have to write down the derivative equals 0. You can't just, okay, on my calculator, I'll do the derivative, then I'll solve it, then I'll plug some numbers in, then I'll find my local max min, and I'll just write down the answer. You can't do it. Can't do it. You got to have the derivative equals 0. Got to see it on your paper. Got to see your stationary points. Got to see your number line. Got to see this. Got to see this. Okay. Use your calculator. Fine if it's a calculator problem, but write down what you're doing and what's going on. Okay. Now let's do the global max min. Okay. So now global max min. We're talking about this stuff over here. Okay. List of candidates. Okay. Very quickly here on 23. It's a pretty simple one. I factored out a 3. Now, what could you do at this point? On this one, you could have done this. You could have added the 3 over there. You could have got this, and then you could have square rooted, but don't forget the plus minus, right? Or you could do what I did, was take out a 3, and then you could factor this, x plus 1, x minus 1. You could do that, and then either way, that gives you these stationary points right here, 1 and -1. Okay? And the 3, of course, doesn't matter. 3 doesn't equal 0 ever, so you wouldn't mess with that. So just 1 and -1. Now, if you had a 3x out there, yeah, then you'd have x equals 0 as another point, but it's just 3. and 3 doesn't ever equal 0. So our stationary points are plus and minus 1, and our endpoints are 0 and 2, so I'm going to plug those into the function. Okay? Now, if this was a calculator one, and I told you that you probably should think of it as no calculator, do them all as no calculator, but I was talking to Patricia. If I was doing these problems from here on out, and practicing for the quiz, I would probably do them no calculator as best I could, unless I was told it was a calculator problem. I would do them no calculator, but then at the same time, I would double check with the calculator just so I'm comfortable doing both ways, because you're going to have to be able to do both. So if this was a calculator problem, and I had to go back here and I had to now plug these in. Now you still want to have all this on your paper. You still would need this on your paper. Now if we did a solve, if I told the calculator to just solve that, that's fine. I can tell the calculator to solve it. Okay? But yes.
Well, you need the negative 1 since it's not each trig.
Oh, thank you. Thank you. Very good. So I get plus minus 1. Our interval is just from 0 to 2. So we would throw that out. I know you're never going to believe me. I did put that up there to talk about that. I was going to kind of keep going with that. But I did that yesterday. I made this up yesterday. I kind of forgot. That's why if you hadn't said anything, I don't know that I'd have caught that. So, yes, we would throw out the negative 1 because it's not inside of our interval. Okay, now that's interesting you said it. Actually, we would have just caught it because what I was just about to do was show you on the calculator. So, just to remind you, and if you want to get your calculators out and look at this, just to remind you to solve, right, it would look like this. So if I was going to solve this equation, equals 0, comma, x, and then since we're only wanting to solve it between 0 and 2, remember with the trig ones, and we are going to talk about trig ones today, so that's going to be really important. Matter of fact, that's the one that is tricky for a lot of people, it seems like every year, just because, we're not everybody's as comfortable with the trig values as we need to be, but this is where we use that vertical bar outside of the solve, and we were doing it with sine like to be between 0 and 2 pi, right? Well, this is the same thing. We want to be between 0 and 2. So I can go less than or equal to x less than or equal to 2, and then tell it to solve, and then it just gives me that 1, right? So it doesn't give me the negative 1. So that's actually nice. So if this was a calculator problem, then we would have had this, and then we'd have just had x equals 1 as our stationary point like that. We just wrote that down because our calculator solved it for us. Okay, but if it's no calculator, we'd be doing this work and we'd be finding it. Then we'd have to remember what Will said to throw out the negative 1. Okay, now we need to plug those in. Now remember, you got to plug them into the original. It says f of 0, f of 2, f of 1. We'll plug them into here. That's pretty easy to plug into, just in your head. But let me show you what you can do on your calculator. Now there's multiple ways we can do this on a calculator. Okay, one way, let me just show you a couple here. I don't want you to get confused by this. If you're somebody who's like, the calculator, I don't like messing around with it too much. I get confused on what buttons to push. And I would just probably, if that sounds like you, then when I go to put a 0 in here, I would probably just type 0 cubed minus 3 times 0 plus 5, or let's pretend it was a negative 2.7 we were plugging in, something weird. I would probably go negative 2.7 cubed minus 3 times negative 2.7. I would just do that every time just to be comfortable. But some people are kind of nerdy like me, and they like to, mess around with the calculator. So if you think that's you, then let me show you what you can do. So what was that original function? It was x cubed. Then what? Minus 3x plus 5. Then you can put that vertical bar. Now notice I didn't do a solve here. And this is where it gets confusing, so unless you really feel comfortable doing this, I wouldn't mess with it. But I didn't do a solve here. What I'm doing on this one is I'm just telling the calculator, hey, I want to do this with, the vertical bar means with. Here we want to solve this with x being between 0 and 2. Here I want to evaluate this. I want the calculator to figure it out with, and then I'm going to put x equals 0. And I get a 5. Now, what's the advantage of that? Well, the advantage of that is I can up arrow, hit enter, and it brings that back, and then I can just delete the 0 and now plug in a 2. And then I can up arrow, hit enter, bring that, whoops. I can up arrow, bring that back. Oh, darn it. That's not what I wanted. I got that 7 in there. Now I can up arrow, bring that back, take out the 2. What's the other thing I wanted? 1. And there I got 5, 7, and 3. So I got 5, 7, and 3, right? And so there's my max, and there's my min. Like that, right? Now, that's one way to do it on your calculator. Now this is where it gets kind of nerdy, I guess you might say. I don't know if you want to do this, but I can plug all 3 of those at once using the curly brackets. See above the, I can't even see which is which. Which one's the curly brackets? Is it above the right one? So I can go here, and I can put in 0, comma, 1, comma, 2, and it gives me 5, 3, 7. And so now I can do them all at once, and so 5, and then of course I did those others over 5, 3, 7, right? So I can plug in like 3 things into there all at once, right? Which is kind of cool. And then of course the other thing I could do with the calculator is I could have defined f of x to equal this, right? I could have defined f of x equals x cubed minus 3x plus 5, and then I could just type f of 0, f of 1, f of 2, and it would have just done that. So there's a bunch of ways I can plug numbers into something. And then there's, of course, the old-fashioned way, just 2 cubed minus 3 times 2 plus 5, and just type that. So I don't want you to get confused with this, but whenever we're doing it, but think about it. Think how often we have to do that. If we're doing a calculator, we have to do a list of candidates. We have to plug some numbers in. When we're doing a number line, we have to plug some numbers in. You know, if it's a calculator problem and it's a complicated function, which is what we usually say for the calculator problems, you know, you have to plug some numbers in. You know, you got to think about how you're going to do that on the calculator. All right. Anyway, let's talk about 25, because here's where the algebra gets really weird. So the original function is this. Okay, the original function is this right here. So, of course, right away, when I write that down, I'm going to write it as powers, because we know we've got this power rule for derivatives. So I'm going to bring the 1/2 down in front, make it that. I'm going to bring the -1 down in front, makes it positive, drop that to a -2. I've got to now solve this. If this is no calculator, and I don't know how much we're going to have to do with this in the quiz. I mean, maybe. I mean, there's definitely going to be some where it's nice, easy algebra like this. Okay? Because I don't want you to get it. It's not an algebra quiz. I want to make sure you can do this stuff, the calculus stuff. But, right, you're calculus students. You got to be able to do algebra. So this could be on there as well. So how do we do this? Well, first of all, in this form, if we're just doing the derivative, I'm fine with you leaving this. But one of the things I told you last week is sometimes you're going to want to then do more with that. You're going to have to be able to rearrange it. So I would move this down to the bottom and put it in the square root, because that's what you would get. You move it to the bottom, x to the 1/2, which is square root. And then I would also move this down to the bottom, because they're just a lot easier to work with when you have positive powers and so forth. Now, when you do that, we now want to solve that. Well, I want to get x by itself, but I can't really do that. And so what I would do here is bow tie this. So I would bow tie this. So 1 times that, that's x squared. And then this times this, that'd be 6 square root x. All over. And then your final bow tie here would be 2 square root x times x squared. Which we can add those powers together for 1, 2, whatever. Now, why did I do that? Well, it's much easier to do a single fraction. Now, this is important. Where is the derivative equal to 0 in a fraction? When, take it back. When is a fraction ever equal to 0? When the 0's where? On top. Okay? A fraction is only equal to 0, like 0 over 4, 0 over 7, 0 over 6, 0 over 2. When you have a 0 on top. Now, we also have to look at the bottom here, which we'll look at in a minute. When is the top ever 0? So this question really comes down to this case. When is this ever 0? Well, now you're still thinking, gosh, I can't really factor out anything. There's nothing, right? And that's true. So you have to think about this. Well, is this ever, What do you know about x squared? It's always what? Positive or could be 0, right? If x is 0, let's just think about if x is 0. You'd have 0, square root of 0, 0, 0 plus 0, 0. So x is 0 would work, right? But what happens down here if x is 0? 0, it's undefined, right? 0, 0. Now what you're getting is the derivative is undefined, which of course could be a sharp point, which could be a max, but we're not going to get into that right now, so don't worry about that. But 0 is not even in our interval, right? Matter of fact, the original function can't be a sharp point because look at our original function. Is 0 even in the domain of our original function? You can't have a local max at a point where there is no point, right? There's not even a point on the original graph at 0. So x can't ever equal 0 anyway, so we can just ignore that. So, but this is always positive, right? What do you know about square root of x? What's square root of 9? Careful now. It's 3. It's not plus or minus 3, right? Square root of 9 is 3. Square root of 4 is 2, right? Right? This, if you have this, now that's plus or minus 3, yes, right? But if I just ask you what's square root of 9, the answer to that is 3, right? So square root of x is always what? Positive. Positive plus a positive ever going to equal 0? Never. So, no solution. There are no stationary points. The derivative is never equal to 0 on this graph. Now remember, let's back up. What were we trying to do? We were trying to find the global max at mid. Well, that happens when the derivative is 0 or at the end point. So what's our list of candidates look like? 0.25 and 1. That's all we plug in. That's it. Okay, now it's 1/4. That's right. Since this is no calculator, we want to put in 1/4. So 1/4, what's the square root of 1/4? 1/2. Square root of 4 is 2, right? 1/2. And then this would be 3 over 1/4. What's 3 over 1/4? 12. So 1/2 minus 12, that's negative 11.5. Right? And now let's put in a 1. So square root of 1 is 1. 3 divided by 1 is 3. So 1 minus 3, negative 2. So there's our minimum, and there's our maximum. Right there. But, yes, it's expected that you can handle that algebra. That's just algebra, right? The derivative is the calculus part. Getting down here to seeing that there's no solution, that's algebra. Now, it's tough algebra. I get it. It's not algebra you've done for a while. So, you know, I understand. And then, of course, it could be a or it could be a calculator one. So if this was a calculator one, we would just type this in the blue up here. We would just type this in and tell it to solve, and it would probably tell us no solution or false or something like that. If it says false or whatever, that would mean no solution. Okay? All right. Let's go back to this 3, 3 times. So that's you know, we're gonna talk some more about these max min problems, working those out. All right. As we run through these, I just want to go through this quickly. This is So Will, you understood that's little f, right? It says big F is an antiderivative of the function f shown below. So little f is what's shown here. They also told us that big F of 0 is 10, okay? And that L is the tangent line at x equals 0, okay? So if they talk about L, they're talking about tangent line. Okay, what is the slope of big F at 4? Well, that's F, big F prime. Well, what's big F prime the same as? Little f. So they want to know what little f is at 4. So all you do is you go over here to 4, you read up, and I don't know, what's it look like? 5? It's just that point. It's just 5, right? So there you go. Where is big F increasing? Big F is increasing. Big F is increasing when big F prime, which is little f, is positive. When is little f positive? All the time. 0 to 10. This graph is positive all the time. So you got to know what they're talking about. But notice how I'm writing this. Notice how I wrote f prime is equal to f. You want to get in the habit of doing that. Because if they give you a little f graph and they ask you about big F, you can't be talking about little f when their question was about big F unless you've made a connection to those. So now it's not like you have to write it down in every problem or in every one of the questions, But somewhere there, if this was a question on the test, you'd have to write that big F prime is equal to little f. So you got that connection. Okay, number 5. Where does big F have points of inflection? If we go to the chart, big F, if this is big F up here, okay, if this is big F up here, big F has points of inflection when we switch these columns. Now remember, this is little f right here, right? So big F switches concavity when little f goes up to down or down to up, right? Maxes and mins. So little f, so that's going to be here and here, right? So big F has points of inflections at 1.14 and 8.19 because that's where little f, which is big F prime, switches from increasing to decreasing, vice versa. Where is big F concave down? Big F will be concave down when little f is, did you say decreasing? Or when little f prime is negative, right? But it'd be when little f is decreasing. Well, that'd be from 1.14 to 8.19, right? Fits with what we just said. So right here, big F would be concave up, concave down, and then concave up, okay, because of the increase and decrease. Why? Estimate big F double prime of 5. Well, big F double prime of 5 is the same as little f prime of 5, like that. Well, that's the slope of this graph at 5. So draw on a little tangent line and get your answer right on. What'd you have? -1.5 is what they have to look at. Why does F double prime have its minimum value right here at the at there? Well, F double prime, remember, is the same as F prime, which would be the slopes of this graph. Where are these slopes a minimum? Well, positive is bigger than negative, so negative slopes are going to be littler, and the littlest negative slope is where it's the steepest, right? Where it's the most negative, right? So right there is where it's the steepest. So the most negative 10 is littler than -9, right? -9 is littler than -8. So that's why it's a minimum. Does a tangent line lie above the curve at 1? Well, now you got to understand, when does a tangent line lie above the curve? When the curve is concave down. So this question is, does the tangent line lie above the curve of big F, is like asking, is big F concave down? That's what they're asking. Well, big F is going to be concave down when little f is decreasing. At 1, is this graph decreasing? No. Okay, so again, you got to go back to the chart. You got to go back to the chart. Big F is going to be concave down when little f is decreasing. Okay? Is it possible that big F of 5 equals 5? Well, now we kind of come back to this, right? Big F of 0 is 10. So if I was going to draw a big F graph, I'm starting up here. Now, what did we say about big F? It's always increasing because little f is always positive, right? Well, there's no way we can go over 5 and go down 5, right? There's no way we can go over 5 and down 5. No way. So it's a speed limit law, right? Can't be. Okay? But could big F of 5 be 15? Could you go over 5 and go up 5? Well, no. 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 Because this graph, little f is the slopes, right? A big F between 0 and 5. What are those slopes? Way bigger than 1, right? If you go over 5 and up 5, that means you have a slope of about 1. What are these slopes? 7, 6, 5, right? They're way bigger than 1. So there's no way you can go over 5 and up 5. It's got to go way steeper than that. Matter of fact, just between 0 and 1, the slopes are above 7. So you go over 1, you've got to go up at least 7, right? So you're already up above that well before you get over to 5. So you're going way too fast, right? It's like I drive 100 miles an hour, and I drive for an hour, and I go west, so I am going west, but an hour later, could I be in Elm Creek? Not if I'm going 100 miles an hour or faster, right? And I drive for an hour, there's no way I'm in Elm Creek, right? I gotta be way farther than that. Because we're going way faster, and that's what that's saying. Okay, all right, so that's more time I want to spend, but that's probably okay. All right, on these other questions, there's a few that we can talk about a little bit, but 35, suppose h is an antiderivative of 3x squared. Explain why it's natural to guess. Well, okay, we talked about this a little bit. If you got h is 3x squared, then the antiderivative we know has to be an x cubed, right? It's got to be an x cubed, and there's probably going to be some number in front. And then we talked about how you always want to tack on some constant. We call it c, but whatever, right? There's going to be some constant, so you know that it has to go one higher. Then it says find the values of a and b such that h prime of x is equal to h for h of 0 equals 1. So let's go through this, because this is what we'll actually do. So I give you h as this. So we know we're going to raise the power up 1 and then divide by that power, right? So big H of x is going to be 1x cubed plus some constant, right? Which they already call b, so let's call it b. So we already know the a's got to be what? The a's got to be 1, right? Because we know that's what's going to be in front of there, right? When we do the derivative, of course, the b will drop out. But now they told us this. So now that means you just plug a 0 in for x. So 1 times 0 cubed plus b. And they said that's got to equal what? That's got to equal 1. So let's just plug a 0 in for x, and that's got to equal 1. Well, 0 plus b, so we get b equals 1. Okay? So what that tells me is my function is x cubed plus 1. That's my function h. Okay? And now when you do the derivative of that, what do you get? 3x squared. Right? 3x squared. So what we said yesterday is when we do the antiderivative, we have to tack on a plus c. There could have been some constant there. We don't know what. Think about that graphically. When we had an f prime graph and I told you to draw the f graph, we didn't know where it was, right? We didn't know where to draw that original graph. But if I give you a point, that locked it in, right? That gave you a place to start. Now you would have a better idea of the original graph. Well, that's all we did right there. That's all that was about. Okay? What was next? 44. Okay. For which value of x does the slope take on its largest value? Well, that's just like doing a max problem, except they want the max slope. Well, what equation gives you slope? What equation gives you slope? No, that's the tangent line equation. That's the equation alone. What? The derivative. Y prime is what gives you slope, right? So what they're saying is, okay, if y is equal to negative x cubed plus 3x squared plus 1, the slopes of that are going to be negative 3x squared plus 6x. What they're saying is find the max of that. Well, how do we do the max of any function? How do we do the max of this function here? We did the derivative, set it equal to 0, did a number line, right? Well, you do the same thing here. We're going to do the derivative, which would now be the second derivative, set it equal to 0, do a number line, it's going to come out to be 1, right? You're going to get x equals 1, and do a number line. Now this is going to be y double prime, right? And so we put in a 0, put in a 2, so you put a 0 in here, you get a positive, put in a 2 in here, you get a negative, and so that's a max, right? Now you can do list of candidates too. They don't, but the problem is they don't really give you any endpoints. And so here's a good time to talk about this, I suppose, is this is a local max, they don't give you any endpoints, so what would your list of candidates look like? Since you don't have any endpoints, your list of candidates would only have one thing in it, right? It would have this 1. Well, how can you make a list of candidates if you only have one thing? Well, here we know something about negative x cubed. It's going to come down, do this, do this. Now, where's the largest slope going to be? It's going to be right there. Well, isn't this kind of what I'm finding right here is the inflection point? I mean, look at it. I'm doing the second derivative equals 0. That's what we said way back here. The second derivative equals 0, do a number line, that's your inflection point. So what we're finding is that this is inflection point. It changes from concave up to concave down. And so that's where it's going to have its largest value. Okay? We talked about that on that other question, where the minimum value, back on that one graph. Okay? So that's kind of what that one, and we'll skip 46 for right now. And let's talk about 54. And again, I don't want to go through it because we got some other ones I want to do here. But it says a particle moves on the x-axis in such a way that its position is given by this equation. So it's given by this. Now we may come back to this another day when we're reviewing for the quiz. This would be a good one to review for the quiz too. So we may come back to this problem later. But you get this. This is its position. So this is like the Bismarck problem we talked about yesterday. East is going to be positive. West is going to be negative. So when it says, when is this moving to the left? What do you want to do? Just tell me the process here. We want to know when the velocity is negative, right? So this is just a chart question. When is it moving to the west is when the velocity is negative. So you're going to do the derivative. Okay? Da-da-da-da-da. You're going to set it equal to 0. You're going to get some t values, right? You're going to put them on a number line, and you're going to see when it's positive and negative and when it's switching. Okay? So I'm going to leave that for you to do because you should be able to do it just fine. Now, did anybody have trouble solving it? If you get 15t to the 4th is our algebra the problem. We get squared plus 60. Wouldn't that be it? Okay? Take out a 15. You'd have t to the 4th minus 5t squared plus 4. And now do this. Isn't that t squared and t squared like that? Minus 1 minus 4. Isn't that how that would factor? Maybe that was right. This would be your derivative. Take out a 15, so you get this. Factor that. Now you get answers for these. Right. This would be plus or minus 1. Plus or minus 2, right? So we got negative 2, negative 1, 1, 2. I don't know, it might have said t greater than 0. It said t greater than 0, so we don't have to worry about those. Right, so we're starting at noon, so we can ignore the negatives. So this would be your x prime number line right here, right? Be the velocity. But it's just a chart question, just like 19. It's exactly the same as 19. Just what we talked about yesterday, right? When is the vehicle moving to the west? It's when the velocity is negative. So you just need to do your chart and go. Same exact problem. So it's another good one to practice for the chart problem. All right, here's what we need to do next. Get your notes out. All right, we need to write down here we need to write down, this would be a good place to start a new page maybe in your notes for these derivative rules. Okay? We need to, because we're going to add to it here today, and we need to get kind of organized here with writing a list of these rules. So as of right now, we've got, of course, probably our most famous one, the most useful one right now is a power law. Right? We've got that guy right there. Okay? And of course, we've talked about sine x is cosine x. And we've talked about e to the x is what? Just e to the x, right? So those are probably our most famous rules that we have at this point, right? Now, let me fill in some other rules that we have. We have the rule that says, I don't know how much we want to, well, let's write these in. We have a rule, we haven't formalized it, but it basically says if you're doing the derivative of functions added or subtracted, so that's like when we have x cubed plus 3x squared plus 2x plus 7, that's like adding that's like adding 4 little functions together. We can just do their individual derivatives. So it's just f prime of x plus g prime of x. We can just, right, that's the rule that just says if you're adding functions together, then you can just do their individual derivatives, because that doesn't work when you're multiplying. It doesn't work when you're multiplying or dividing. So it is an important rule. Okay, then we also had the rule that said if you've got a number sitting outside of a function, like just a constant k, so like if you have 2 sine x, then that k just sits there while you do the derivative. So 2 sine x, the derivative would be 2 cosine x, right? 2 sine x, the derivative would be 2 cosine x. And then we had that rule that if you multiply on the inside, if you have f of k times x, so if you multiply on the inside, what do we say you have to do with that? Keep it on the inside and kick it out too. So the derivative of that's going to be k times and then f prime of k times x. So you leave it in, you do the derivative like normal, then you kick it out also. So those are kind of the rules that we have so far to be able to do these derivatives. Okay? Now we're going to add to that list here in a little bit. Okay? All right. Now, I just kind of threw this in here. Solving, I've already assigned these, I think, at one point. If you want to just jot this down somewhere to yourself, here's a couple of IXLs, just practice on solving. You're going to have plenty of homework to be doing this week. But as we get ready for Monday's quiz, there's some practice in just solving exponential log trig equations on the IXL, those two right there. So obviously that is something we have to be able to do, is solving those. Of course, the one we just did, the algebra one, maybe we should practice some algebra ones too, factoring. There's some factoring practice and stuff in there too. I guess I haven't looked it up, but I just assume that's the easier stuff. But, all right, don't write this down. I want to go through this with you. I want to talk about this e to the x. Somebody in the other class, Trey Ruby, I think, had asked, why is e to the x its own derivative? And I just said, well, just trust me, it is, but it's the slopes of it are always the same as the y value. It just is. Well, why is it? Well, remember, we can always go back to the definition of the derivative. We can always go back to the definition of the derivative to do one of these. And that's, of course, remember last week. Now, you're not going to have to do this. Don't write it down. But you're not going to have to do this on this quiz. But we can always go back to the definition of the derivative. So if I wanted to do the slopes of e to the x, the derivative of e to the x, I can go back to this, right, that we did our last quiz. So plug an x plus h into that function. You would get that. And plug an x into that function, you'd get that, right? It would look like this. Now, the problem with this is there's no algebra, obvious algebra that we can do, right? Well, one thing we could do is we could go to our calculator, and this is what you probably saw I had on here. I could just let the calculator do it, right? So I could do, I'm sorry, I did that wrong. That's not what I wanted to show you yet. That's not it. I could, because our calculator is so smart, I could just have the calculator do that, right? But that's kind of cheap. How does it do it? Okay, so there is a little bit of algebra I can do right here. This thing in the blue, wouldn't it be true that I could make that into that right there? Right? Because what do? When you multiply, you add the powers, right? So wouldn't this be the same as that over there? Okay? And so then when I do that, right? When I do that right there, now I can factor out e to the x. Okay? Now, just try to focus on one thing at a time here. So now up here I can factor out e to the x, right? So I factor out e to the x and I have this. Now, as h approaches 0, this isn't going to change, right? Because h isn't even in it, right? So e to the x is not going to change. So I could rewrite it like this, right? As h approaches 0, it's kind of like having 2x over 3. I could write that as 2 times x over 3. You see what I mean? I can just bring that 2 here. So as e to the x, I can just kind of bring out in front here, and then e to the h minus 1 over h, do that, right? So now, as h approaches 0, again, this is going to be unaffected. But this is the thing I got to look at. What's happening to this as h approaches 0, right? Well, it's obviously we can't plug in a 0. E to the 0 is 1. 1 minus 1 is 0 over 0. We get 0 over 0, right? So what does that mean? Keep going. Do something. Well, I went ahead and did something here. I went ahead and just had the calculator do it, and I got 1. Or remember what we did with our table? I went ahead and did it in a table. Remember when we did that? And sure enough, as x approaches 0, this seems to be approaching 1, right? See in the table? Okay, so back to this. Sure enough, this part of it just equals 1, and so we get e to the x, right? So that proves it. That proves that the derivative of e to the x is e to the x, because we sent it through our slope thing. We sent it through our slope definition, okay? So just a little side note there, but that's why in this derivative rule, that's why the derivative of e to the x is e to the x. We could do the same thing with sine, okay? And we could run it through and pull up some old trig formulas to help us simplify it, check some limits in there, and we would find out that's what it would be. Okay, it just be interesting if you want to mess with it yourself, but you know, otherwise don't worry about it. All right, so those are my rules that we have so far for this. All right, so now let's go ahead and add. This is where we get into section 6 and 7 now. So section 6 is the trig section. So 2.6 is the all about trig stuff. I might have that backwards, actually. Yeah. 2.6 is the e to the x and log section. And 2.7 is the trig section. Now, all that is, so we're skipping 2.5 for right now. So all that means is those two sections are going to talk about all the same stuff we've been talking about. Local max min, global max min, that stuff. But just with these functions instead. Okay? So we have some things to add. So, for example, we need to add the rest of our trig functions. So, cosine. The derivative of cosine is negative sine x. Kind of interesting. The derivative of sine is cosine. The derivative of cosine is not sine, but it's negative sine. Okay? And the derivative of tangent is secant squared. Just going to have to memorize those. I guess I did put tangent in here, so, which is fine. I was just going to say I don't think I'm going to ask you about tangent, so you don't have to really worry about it, but let's just put it down there, that's fine. Okay, we just did derivative of e to the x, so now let's look at, let's make sure that's let's not worry about it. Tangents. Yeah, there it is. Okay, so the derivative of a different base. So instead of e to the x, what if you had 2 to the x? Or what if you had 3 to the x? Well, it turns out it's very similar. It's its own derivative times a multiplier of ln of the base. So, in other words, the derivative of 2 to the x would be 2 to the x times ln2. You have to tack on an ln2. Now remember, ln2 is just a number. ln2 is just a number, right? So it's 2 to the x times this number ln2. 3 to the x would be 3 to the x times ln3. And to be honest, e to the x is actually the same thing. This would be e to the x times lne. What's lne? lne is 1. So that's why we don't throw it on there. So it's actually a special case, which is one more reason why e to the x, e is a special number, right? So e to the x times lne, lne of course is just 1. Okay, so that's another derivative rule. And then I'm going to run out of room here. Natural log. What's the derivative of the natural log function? Well, it turns out it is simply 1 over x. Kind of interesting. That is an exception. That is an exception to the, think about it. Most algebra equations, the derivative is another algebra equation. The trig equations, the derivative is another trig equation. The exponential equations, like 2 to the x, the derivative is 2 to the x times ln2. It's another exponential equation. Log is an exception. The derivative of ln x is 1 over x. There's no log in it. Okay, and then I'm out of room, so I'm going to go to the next page. And the derivative of other base logs, so log base a of x is very similar. It's still 1 over x times 1 over ln a. So again, it's very similar to the exponential. Remember, exponential logs are inverse functions. So there is this kind of this connection. So if you were going to do log base 2, and you were going to do the derivative, it's 1 over x times, and then it's 1 over ln2. So it's log base 2. You have to tack on this 1 over ln2. So you just have to memorize that. We don't run into those very often. We don't run into 2 to the x's and those kind very often, a little more often than those logs. Most of the time we're dealing with ln's and e's. Okay? All right. So those are just going to have to be memorized. Okay? We're just going to have to memorize them. So what's an example? And on this next quiz, there's going to be a little bit of this, like you could have a problem like this or a couple problems like this, where I just want you to do the derivative. Okay? So let's do f prime. Okay? So I'll let you write that down. All right, so what do you think? What's the derivative of 3x squared? 6x, that's easy. What's the derivative of sine? What do we do with that 2 in there? Kick it out and leave it in. So we get 2 cosine 2x. Right? Plus, now, what did we say? And this is the one people still want to do with the power. We don't bring this power down. When there's x's up here, you don't bring, that's not the power rule. Power rule is only when you have x raised to a power. When you have a number raised to x's, that's an exponential function. So that is this example right here. That is this example right here. 3 raised to the x, okay, is that. So what would this be? We always keep the inside the same, times ln of 3 times what do we do right here? No. What did we kick out? We had to just kick out the whatever was being multiplied, because that was going to squeeze in, right, and make the slope steeper by a 2 factor. Whatever's multiplied by the x, we have to kick that out. So we have to kick out a 4. The 4 is multiplied by the x. So that's that other rule. That's that old rule we had. We still have that rule. So what rule are we using? We're using the rule that says a to the x is equal to a to the x times ln a. Right? So that's why we got the ln3 there. We also have the rule that says you leave the inside alone, and if there's something multiplied by the x, you have to kick it out. So we were using a combination of those rules. And we were actually also using the rule that said if you're adding functions together, you can do their individual derivative. So you use a combination of those rules as you're doing it. There's your derivative right there. Okay, now let's really make it interesting. Let's do the second derivative. Okay? Which just means do the derivative again. So what's the derivative of 6x? 6. What about this one? What do we do? What do we do when we have a 2 hanging out in front? Just leave it. What's the derivative of cosine? Negative sign. So this turns to a plus. And what about this 2 on the inside? We got to kick it out. And plus that 2 is still there, so what's on the outside? There's now a 4. This is now sine, and the inside always stays the same. Right? So the derivative of cosine is negative sine, which is going to turn that to a plus. We're going to kick out a 2 to go along with the 2 that's still sitting there, and the inside has to stay the same. Oh, what about this one? Now remember, ln3 is just a number. So ln3 and 4 are kind of like this 2. When you got a number sitting on the outside, it just hangs out there. So this ln3 is just going to hang out there, and the 4 is just going to hang out there. Right? We're not going to do the derivative of the ln3. We're not going to be doing this. ln3 is not a function. ln3 is a number. Right? ln3, I can't say this more too many times. ln3 is just a number. lnx is a function. So lnx and ln3 are not the same thing. lnx we do the derivative of. ln3 is just a number. What's the derivative of ln3 then? It's just a number. What's the derivative of just a number? 0, right? The derivative. What's the derivative of pi? 0. What's the derivative of e? 0, right? Not e to the x. I said e. The derivative of e is just 0. E is just a number, right? So understand. Okay, anyway. These are just numbers. They're sitting there. So they're going to just sit there, right? They'll be in the answer. So all we're doing is a derivative of that. Well, we already did that once, right? Well, what's the derivative of that? It was itself. Then we had to tack on a ln3. Then we had to tack on a 4. And we still had those sitting there. Right? Now, you're right, I could 4 times 4 is 16. ln3 times ln3, I could make that ln3 squared if I wanted to, right? But did you see what happened there? These are just sitting there as numbers, multiplied, so they just hang out. I do the derivative of this, I got to do the same thing I did when I did it before. Do the derivative of that, it's itself, times an ln3 tacked on because of this rule, and then I got to kick out that 4 because of that. And then I've got those things that are still just sitting. No. Because, okay, that's different. Now, you're right. Here's what Emily's saying. I just got him saying the derivative of a number is 0, right? But that's if I'm just doing, 3x plus 7. When I do the derivative of 7, I get 0. But when I do the derivative of 3x, I don't make that a 0. Because that's different. I have a number times an x, so it just hangs out there, right? So I'm not doing the derivative of these numbers. If I have this problem, here's the one that always gets me. If I tell you to do ln x, if I gave you this function, okay, and you tell me the derivative, what's the derivative of ln x? 1 over x. Plus, now, Emily, I'm doing just the derivative of ln3. Here, I wasn't doing the derivative of ln3. It was a number tacked onto this function, right? But now I'm doing the derivative of ln3. What's the derivative of ln3? 0. Now, people want to put 1/3 there, right? They want to put 1/3 there, but it's not. It's just 0. Okay, here'd be another example. So if I had ln3 times x squared, Emily, right, what would be the derivative of this?
2x times ln3.
Yeah, or bring the 2 down in front, 2 ln3, right, times x, right? Either way, what you said, right, 2x times ln3. The ln3 just hangs out there. You bring the 2 down, right? It's just a number in front, so it's different. Here you're doing the derivative of ln3. Here you got ln3 times a function. It just hangs out there. Okay, so that's the difference. All right, well, you'll get to practice some of those in the homework. Now, where it really gets really interesting, but we're not going to have time to do it, you're going to actually try some on your homework, and then we'll talk about them tomorrow. What's big F of X mean? Antiderivative. So you gotta go backwards. Now we already did that with the power rule. But let's just do this one right here. What must this have been? And that's how you have to think of it. We don't have an antiderivative rule. You have to think, what must this have been so when you did the derivative you got sine? It must have been cosine, right? And we always leave the inside alone, so there had to be a 2x in there. But what's a derivative of cosine? Isn't it negative sine? The derivative of cosine is negative sine. So what sign must have been on this out here? That must have been a plus, right? Because it was cosine, do the derivative would have given me this negative. Now wait a minute, when I do the derivative, aren't I going to have to kick out a 2? How come there's no 2 here? There must have been something here that canceled that 2 when I kicked it out. What must have been there? There must have been a 1/2 sitting here. But that, remember we talked about that yesterday, that's how you have to think about an antiderivative. You have to think, what would it have been so when I did the derivative it gave me that? So you say, well, it had to be a cosine, and the derivative of cosine is negative, so this must have been plus, so it made the negative. The 2x would stay the same, but when I do this derivative, I'm going to kick out a 2. There's no 2 sitting here, so there must have been something there that canceled it, so there must have been a 1/2 there. That's how you have to think of those antiderivatives. We're going to do a lot of those after Christmas. You're not going to have to do too many of those, but there's going to be some on the homework, just some basic ones. I know they doesn't seem real basic right now, but as you do some, you're going to, okay, so those are derivative rules, so we're going to be kind of working on those as we go along here over the next several days as well. All right, so last problem. Let's go ahead and do this. One of your homework problems today is very much like this one. So once again, on one of your homework problems today, you're going to be able to just kind of follow this script, okay, that we have right here. Oh man, it's been bad days to be sick. All right, so here's what we're doing. This is on page 147. The question says, does F have any stationary points? Where is F increasing? Find the max and min values, which means global max min values. Where is F concave down? All that stuff. It's asked everything. The question basically wants all that information. What's the chart stuff and what's global max min and what's everything. Well, okay, so where do we get started with this? How do you start? This is no calculus. We're going to find the derivative. Great example of a problem. I said you don't know where to start. Do the derivative and set it equal to 0. Right? Do the derivative and set it equal to 0. Okay? So f prime of x equals 1 what's the derivative of sine? So it'd stay a minus, wouldn't it? So yeah, now you're going to have to start thinking of that because the derivative of cosine is negative sine, right? So it would have turned to a plus if we were doing cosine there, but we're doing sine, okay? And then when I say set it equal to 0, okay? All right, so then we solve that. So add cosine over to the other side. Cosine x equals 1. Where does cosine x equals 1? And I do believe this problem, in all of the questions, they ask it between 0 and 2 pi. Okay? So this would be a no calculator one. Now we're going to do some trig ones that are calculator ones also, but this is a no calculator. Okay? All right. So, where does cosine equal 1? At 0 and 2 pi, right? So, once it asks about increasing, it asks about stationary points, it asks about decreasing, right? So that's going to be, what am I going to do to get those, answer those? Number line. So I'm going to go over here, I'm going to do a number line. Now the problem is, for max min, we said, or for local max min, we said we didn't want it to be an influence, right? And it doesn't ask for local max min anyway, so it doesn't really matter. Okay, but so now what would be a number in between 0 and 2 pi that'd be good to plug in? Pi. words, because where am I going to plug them? I'm going to be plugging them right here, right? So I don't want to do the cosine of 1 or the cosine of 2. I want to do the cosine of pi or pi halves or something like that, right? So what would be a good number to plug in that's bigger than 2 pi? Now I know it's outside the interval, but we need something over here. How about 3 pi? Were you saying 3 pi over 2? That's not past 2 pi. So something like 3 pi. What would be something over here like negative pi, right? Those would be numbers to plug in. Right? If I needed something between 0 and pi, I'd pick pi halves, right? Something easy to plug in. Okay, so let's plug those in. So what's pi? Let's start with pi. What's cosine of pi? No. Cosine of pi is -1, right? Unit circle. Pi is over here. Cosine is the x value. It's -1. 1 minus -1? 2. Positive. What about 3 pi? 3 pi would be, where would, 3 pi be that same place? Right? 2 pi, that'd be 3 pi. It's positive. Where's negative pi? Oh, same place. Positive. What's this tell us about this graph? What's it tell us about f? It's always increasing. It's always increasing. What are all these spots? These are all flat spots. They're all flat spots, right? So that, I made this up, and it wasn't a very good one, obviously. I should have thought about it a little harder. But that's okay. That happens. So are there any stationary points? Yes. There they are. Where is f increasing? Everywhere. 0 to 2 pi, right? It's increasing the whole time. Where is f concave? Okay, we'll get to that question in a minute. But then it says, where are the max and min values over the interval? Now, something I forgot to say back on this one. Remember back on this one, and we said that this was always going to be positive right here, right? We were doing f prime. What does that tell you when f prime is always positive? We said there are no stationary points. If f prime is always positive, what's f doing? Always increasing. Well, where do the max and mins have to be if the graph's always increasing? Doesn't your min have to be back here? And your max have to be there, right? So I'm not sure I even needed a list of candidates here. I could have just said, since this graph's always increasing, the minimum value will be at the left-hand point, the max value will be at the right-hand point. Now, if they say find the max and min values, then you need to plug them in anyway, because you got to get the outputs. So the list of candidates is a good idea always anyway, because you want to get those values. Okay, so, but if the graph's always increasing, well, we got the same thing going on here. The graph's always increasing. So if the graph's always increasing, okay, 1 minus cosine is always positive. Actually, that makes sense. 1 minus cosine, that's just the cosine graph flipped it and shift up one. Well, if you take the cosine graph and flip it, the negative, right, would flip it. And then you shift it up one, isn't it always going to be above the x-axis, right? Cosine will always be above the x-axis there. So it's always going to be positive, so that's why the f graph's always increasing. Okay, now it asks about where's it concave down? And where is it increasing the most rapidly? Well, remember, when does a graph increase the most rapidly? At its inflection point. So this is really asking about inflection points. Well, what do we need for inflection points at concavity? Second derivative, okay? So this is our first crack at second derivative. So let's do the second derivative. We'll do that in red. So what's the derivative of 1? 0. And what's the derivative of cosine? No. Well, it's going to be because negative, but I just asked the question, what's the derivative of cosine? Negative sine, but there's a negative in front of it already, so it's going to turn to positive sine. So the second derivative here is just sine. And then we got to set that equal to 0. So where does sine equal 0? Sine is the y, right? Well, that'd be at 0, pi, and 2 pi. So 0, pi, and 2 pi. Okay? Well, it turns out 2 of those were the same thing we had there. Now we do a number line. Now notice how I want to label it. So I got 0, I got pi, and I got 2 pi. Now I'm going to pick some numbers in between. So pi halves, 3 pi halves. We can just do 3 pi over here, but you know what 3 pi is going to be? We better go 5 pi halves. Because 3 pi is just going to be another place where it's going to be 0, right? 0 pi, 2 pi, 3 pi. So that's not going to work like it did last time. And here we better go negative pi halves as well, which you would see that but we're gonna run out of time, so I wanna make sure we just, so I just need to pick some numbers in between. Now, we're gonna plug those right here, right? We're gonna plug those into our second derivative. Well, what's sine of 3 pi halves? What's sine of 3 pi halves right down here? -1, right? What's sine of 5 pi halves, which would be back around up to here? +1. And you can see the pattern. What's the sine of pi halves? Positive. Negative pi halves would be down here. Negative. So what does this tell me about the F graph, that number line I just made? Concave down, concave up, concave down, concave up, right? So it says, so the question, so D says, where is F concave down? Well, now remember, we only want to go from 0 to 2 pi, so I really don't have to look over here, and I really don't have to look over here. Just between 0 and 2 pi is all I really need. So between pi and 2 pi, be concave down, right? And then where is F increasing the most rapidly? Increasing the most rapidly, well, that would be if at its inflection point, right? So here it's inflection points right there at pi, right? So at pi it's concave up, switching to concave down. So that would be this kind of situation: concave up, switching to concave down. So it's increasing the most right there. So F is increasing the most right there, which is at an inflection point. Okay, yeah, I should have picked it. That's okay. You'll get into one that'll might be a little more interesting. But it's got the concave. But that happens sometimes. There's no state. There's no local maximum. What this graph's doing is it's coming up, flat spot, coming up, flat spot, coming up, flat spot, coming up, flat, and it just keeps having the flat spots every 2 pi, and it's just continuing to do it. Okay. Now you notice we didn't do any problems with the e to the x. Think about e to the x and ln x. They're pretty uninteresting when it comes to local max min. So, if you have an e to the x, here's e to the x graph. Here's a natural log graph, right? I mean, they're pretty uninteresting. They've got their concave up or concave down all the time. Their concavity doesn't change. There's no inflection points. There's no local max mins. I mean, so we don't spend a lot of time with max min problems using the e to the x function. So, but they'll ask you some other type stuff with that. Okay, and then you got these problems. These problems here. Oh wait. No, I looked at the wrong 35. Third. No. Let's see. Okay.
the evening?
What's that?
What's the evening for?
Oh, even.
Oh.
I'm sorry, yeah, the evening's even. Yes, sorry.
All of them are just?
Yeah, 16 through 30, even. And then 18 through 34, just the even. So if you need to take a picture of it.
Do you have like decimal answers on like 6?
Probably not. I believe they're always going to be looking for, yeah, just in terms of logs. So you're talking about number 6? Yeah, no, this is pretty much all no calculator. So, hey, I misspoke when I said this, right? Well, I didn't really misspeak. I said this is like number 35 on page 147, which it definitely is. But the number 35 you're doing is not the one on page 147. I misspoke when I said that. The 35 you're doing is in section 2.6. The 35 we did is in this section. That's okay. That's the one I wanted to do. I still wanted you to see this, right? But when I was writing this down last night, I wrote this and I'm like, oh, hey, this is like number 35. Well, it is, but that's not the 35 you're doing on your homework, which is fine. You still should be able to do it. I said, oh, okay, this one's like that one. I'll make note of that. Well, it doesn't matter to me know that because we're not doing it. But we are going to be doing more of these. So you're not going to have a trig one like this to do with Local Max Min tonight. Okay, now tomorrow we will, and we'll do another one in class together. But I want you to see one here. Okay, so anyway, so just in case you're thinking about that when you're doing the homework, I'm wondering. Okay, so Emily, on your question, it says h of x is equal to log base 10x, right? Right, and then it asks h prime, it says use theorem 12. I could care less if you ever call that thing theorem 12. I will never call it theorem 12, okay? Theorem 12 is just the rule for the derivative of log, right? So now here's something you're going to hear me say a lot this year. Before we can do h prime of 1/10, we need to know what h prime of x is, right? So we need to do h prime of x, which according to theorem 12, I will never call it that, the rule for this derivative is what? It's 1 over x times 1 over ln 10. That was our rule for these logs. That's the rule for the derivative of a log function right there. Now, since that's h prime of x, h prime of 1/10 means what? Put a 1/10 in place of the x. Well, what's 1 over 1/10? 10. And then this is 1 over ln 10. So this would be 10 times 1 over ln 10, which I'm fine if you leave it like that, or if you write it 10 over ln 10. So absolutely not, don't use a calculator here. This would definitely be a no calculator kind of problem, right? So, again, the no calculator part of this quiz is probably bigger, longer than the calculator part. So I think, again, most of these problems are no calculator. Now, we're doing the derivative ones, and you want to check them on your calculator. I showed you that, didn't I, how to do the derivative on your calculator? If you want to check them, so right here, you can do under this by the 9, here's the derivative thing right here. And so if I want to do the derivative of, what was that, log? We want to do log base 10 of x, and I want the calculator to do that for me. Oh, that's weird. same as, log base E is the same as 1 over ln 10. That's the same thing. I don't like how it wrote that, to be honest with you. I would never, but let's do a simpler one. So you just want to do ln x, okay? Just want to do ln x, 1 over x, right? So it'll give you those.
Does it give you like that, right?
Well, it says domain may be larger than the domain of the input. In other words, ln x you can only put in positives, right? ln x, you cannot put a negative into ln x. So you can only put in positives, but the answer would accept negatives, right? So they're just saying, hey, warning, this, the derivative is 1 over x, but remember, you can only put in positives, which makes sense. The derivative should always be positive on ln x because the ln x graph looks like this. It's always increasing, right? So the slopes of ln x should always be positive. So they're saying, hey, warning, you can't put any negatives into this 1 over x because there are no legitimate negative values for that. That's all that's saying. So most of the time you can kind of ignore that. It's not a huge deal, but